All right, we're getting started. It's Tuesday morning. We are getting back to work on section 4.1 on related rates. Okay. So we've done a couple of these examples before, but we are going to dive right in and do a couple more today. All right. Does anybody have questions before we get started?
What are related rates?
What are related rates? Good question. Okay. Related rates are when you have some sort of situation where there's variables that are related to each other. Okay. Last time we saw this sort of problem where there was a ladder and the ladder sort of slides down. It's in the videos. In this situation, you have like this distance, which is related to this distance, right? You have like an X and a Y. Or you have maybe the angle theta, which is related to those distances as well, okay? And we have an example in the video of like a circle, which is getting bigger. And as it gets bigger, its radius increases, right? So the radius R increases, but then you've got like the circumference or the area inside the circle. And those variables are related to each other, right? And whenever you have variables related to each other, you can look at the equation that relates them to each other. You can differentiate that equation and obtain and like discover a relationship between the rates of change in those variables. So what we're going to look at today is we're going to look at an example where we have like a cone tank of water, sort of water inside it. And the water is like dripping out the bottom, draining, water levels going down. And we have two variables here. We have the volume and we have the like height of the water. And those two variables are related. We'll also do a problem today where we are standing on the ground and over here there is a balloon or something. Here's a balloon. And the balloon goes up. And as the balloon rises, the angle of elevation, the angle we have to like look up, right? The angle you have to tilt your head, right? That begins to increase, right? And that's related to the height of the balloon. And then we'll discover the relationship between the rates of change in those two variables. So this is what related rates is. Okay. Let's go ahead and get into one of these problems. So first, a cone, like an upside down cone-shaped tank of water has a radius at the top, like a top radius of, let's say, 4 feet. It's going to be a big, nice big cone tank. And a height of 6 feet. Okay. Water is leaking out of the tank at, let's say, 2 cubic feet per hour. Okay, I'm working in feet over here. I'm gonna keep my units the same. I'm working in cubic feet now over here. Okay. And that's per hour. I don't know how realistic this is. That's okay, doesn't matter. And then the question we're going to ask is, how fast is the depth / height, whatever you want to call it, of the water? How fast is that changing when it is, let's say, 3 feet? When that height is, or the depth of the water in the tank is 3 feet? Question. Okay, so let's make this all a lot smaller so we can start drawing pictures and stuff. We're going to work through this in the we're going to work through this in the way that I taught you guys before, to follow these steps called dreads. So the first step in dreads is D, which stands for diagram. I'm going to draw a diagram, and I'm going to label any constants and variables involved in this problem. Okay, so make a nice picture of our cone. There's our cone. Okay, and at the top of the cone, the radius is 4 feet. That's not a variable because the shape of the tank is not changing, right? And the height of the cone is 6 feet. Okay, so there are 2 constants. Those are genuine constants. They're not changing over time. But inside of the cone, we have some water. Okay, so here's water inside the cone, taking up this space right here. Okay, I'll go ahead and fill that so it looks nice and watery. Here we go. So the water has a different radius because it's sort of like a smaller cone, which is inside the big cone, right? There's the cone-shaped tank, and there's the cone of water inside of it. And if it's leaking out the bottom, okay, there's the water leaking out the bottom, then what's going to happen is we're going to have a change in the volume of the water. So one of the variables involved here is going to be the volume of water. And down here, we have changing in volume. Now that means that the height of the water, this height, is also going to be changing. And as the height decreases, the radius is going to decrease. So the radius is a variable and the height is a variable. Okay. So this is our diagram step. Sound good? Any questions? Okay, so now let's identify the rates. do that right down here. We have a couple of different rates of change. In this problem, there is a rate of change that's given to us. The water is leaking out of the tank at 2 cubic feet per hour. If I can underline this. Nope. Being really finicky. There we go. The water is leaking out of the tank at 2 feet per hour. So that is a rate. It means that the rate of change in the volume of the water in the tank with respect to time, so dV over dt, is equal to 2. Although actually, I guess the volume of water in the tank is going to be getting smaller if it's leaking out, right? So I guess I'll write that as -2 feet cubed per hour. So that's one rate involved here. Now, another rate that we would want to know at some point is how fast is the depth of the water changing, okay, when it is 3 feet. So that is an unknown rate. It's the rate of change in this height variable. So I'll write dH over dt equals what? I'll just put some question marks there, right? And then I'll write the words when h equals 3 feet. Okay. I'm not counting how many times the dog comes in and out today, but it feels like a lot so far. Any? Okay, all going okay so far? We've got our diagram, we've got our identified rates. Now, identifying the rates is helpful because it gives us a direction. It tells us, what is the information we know and what is the information we're trying to find out. But now we need we need to get back to this relationship between the variables. We know that the primary variables we care about are the volume of the water and the height of the water. Those are the primary things we care about. So we'd like to see if we can find a relationship between those, okay? Now, for this, we're going to need to look up a formula, okay? We need to know a geometric formula here. There should be a geometric formula for the volume of a cone, right? So if you don't know a geometric formula and you need one, please feel free to look it up, okay? You don't need to memorize all the geometric formulas. Here's the geometric formula for the volume of a right circular cone, which is what we're talking about. So, and it kind of gives the variables here, the height and the radius, with same exact variable names that we're using, thankfully, so we don't need to adjust any letters. It's basically pi r squared h, but then divided by 3. So I'm going to put that over here for the equation step. I'm going to write volume is equal to pi to 1/3 pi r squared h. Okay. So that's a beginning equation to work with. It relates volume to both the radius and the height. Now, I don't really want the radius and the height to be both in this equation. I would rather have an equation that just relates volume and height, right? Because those are really the only variables that I actually care about here. If I can get rid of my radius here, if I can get rid of that radius variable from my equation, that would be better, right? This is where you start looking for other relationships that are involved that you might be able to use to eliminate a variable. And sometimes it comes from something like the Pythagorean theorem. Back in the In the latter problem we did the other day, we had like a situation where there was, we had to do like a trig function and involved one of the sides of the triangles that we didn't actually have. And so we used the Pythagorean theorem to solve for it. That's the sort of thing I'm talking about. It's like other relationships that exist within this scenario that you can rely on to kind of eliminate variables or solve for unknown variables. So in this situation, it's the shape of the overall tank. It is a 4 radius, 6 height tank, and that proportion 4 to 6 is going to remain true even as the volume, as the cone of water gets smaller. It's still going to be a 4 to 6 ratio between radius and height. One way to think about this is in terms of similar triangles. So I'm going to make a second layer here so I don't have to, here we go. So,
can I ask a question?
Yeah, sure.
So as the height decreases, the radius decreases proportionately. Is that what you're saying?
Exactly. Yep, that's correct.
So if the height was like 5, the radius would be like 3, or something like that.
No, that's not a proportion. What you just described there is not a proportional relationship. That's more a linear relationship where like so what you described there is that they're decreasing at the same rate because you subtracted 1 from both of them.
Yeah.
It's more so proportional relationships, more like the percentage decrease is the same. So if for example the height decreased to 3, that's half.
Yep. Okay. I see. Yep. That's what I'm. Yeah.
Yep. And then the radius would decrease to 2. Great. Very good question. Yeah, that's exactly what I'm saying. So that if you're comfortable with that, that's enough. Like we can just stick to that concept. I'm going to kind of show another way to look at it, which is in terms of these similar triangles. So here we have a similar triangle, which is a, 4 here, 6 here, right? But then we have inside this another smaller triangle like this, right? Here's the smaller triangle. And these triangles are similar because they have the same angles. That corner is a 90-degree angle. This corner is a 90-degree angle. And then they both share this angle down at the bottom here, right? That angle. And so that means that this angle must be equal to this angle, right? Because it's the only angle left. If the other two are both equal, the third one has to be equal because they both got to add up to 180. So those, we have similar triangles, and that means that their ratios are in proportion. So we can, going back to our first page here, we can say that the R divided by H ratio is equal to the 4 to 6 ratio. The R to H, the ratio of R to H is equal to 4 to 6 because of that proportional relationship. I'm just going to sort of lower the opacity on that guy there, so it kind of fades away. Okay, so how is this helpful? What this means is we can solve for R. This is a 2/3 relationship here. 4/6 is 2/3, and then that's 2/3 H. So R is 2/3 H, and then we can substitute that into our equation for R over here. So let's see. Now we have volume equals 1/3 pi, and then in place of R, I have 2/3 H. That's squared, and then I have another H. So now we can simplify this a little bit.
So why do you need to multiply H and 2/3?
What?
Why do you have to, so you got R over H equals 4 over 6. R is 2 over 3, but why H? 2 over 3 times H.
Oh, I just multiplied both sides of this equation by H. So
okay.
H here, just to cancel the H out on this side.
Okay, I must have been zoned out a second.
That's okay. Okay, so we're making our substitution into the volume equation that we got from Google there. Pretty soon you're gonna have like an AI chatbot in your phone that you can just be like, hey, Sydney, what's the volume equation of a phone? I guess you kind of already have that with Siri, don't you? Whatever. But then it'll strike up a conversation with you afterwards and be like, hey, why are you using that? Man, have you guys been following this whole AI chat GPT thing? I don't know. Sorry.
You don't use it?
Chat GPT?
Yeah, I ask it very interesting questions.
Chat GPT is nuts. It's an AI chatbot. It kind of creeps me out because it makes me feel like we're living in the future. Yes, freaky is a good word to describe it, Hannah. I agree. In the chat, Hannah put it's interesting / freaky. Anyway, let's do some algebra here. So we're gonna have 4/9 and then also times a third. So we're gonna have 4/27. Okay, I'm working with my constants here. I'm just squaring 2/3 and then multiplying by another 1/3. So that's our constant factor. We've got 1 pi here, and then we're gonna have h squared times another h. So that's h cubed. There's a nice simplified version of our equation there. I'm going to let you look at that for a second and just make sure we're all comfortable with what we have before we move on. Doing okay? Remember, we now have what we want, which is an equation that relates the volume to the height. That's it. And there's no other variables involved because we were able to get rid of radius by making this substitution based on proportions. So great. So now our next step in DREADS, D-R-E-D, is another D. It's differentiate. So now we're going to take our equation here, and we're going to differentiate it with respect to time. So we're going to do like d over dt of the left side, v, equals d over dt of the right side, 4/27 pi h cubed. So when we do this, what are we going to get? On the left side, we just get dv over dt. That's boring. There's no particular function to differentiate there. It's just the derivative of volume. It's dv over dt. That's the rate of change in the volume. On the right side, we can differentiate. So we have 4/27 pi. That's all constant. That's still there by constant multiple rule. But then we're going to take the derivative of h cubed. That's 3h squared. But then because we're differentiating with respect to t, not h, we have to multiply by dh over dt, the derivative of height with respect to time, or the rate of change in the height, basically. Remember, this is basically an implicit differentiation with respect to a variable that isn't even part of your equation. So all of the variables in the equation, both the v and the h, we treat them all the same way we treated y when we first learned implicit differentiation, right? We treat it as if it is implicitly a function of the variable, in this case, t, right? So we have to multiply it by its derivative, technically applying that chain rule every time we encounter anything, any variable. So there's a little bit of simplifying here. 3 goes into 27 9 times, so that goes back to 4/9. So now we have our new equation, 4/9 pi h squared, and then times dh over dt. That is our equation, our new equation that relates the rates of change to one another. Remember what I said at the beginning when Frau first asked, what is related rates? It's where you start with a relationship between two variables, you differentiate it, and you get a relationship between the rates of change in those variables. possibly also still involving some of the variables, like CH is still involved in this equation after we differentiate it. So it's not solely relating the rates of change to one another. It also still involves the H, but at least it relates the rates of change to one another, right? So now we can finally answer our question with the substitute and solve steps. So the substitute step is to substitute in everything we know, which is where this stuff comes back into play. Remember, we know the rate of change in V, that's -2 cubic feet per hour, so we can plug that in. So on our on the left-hand side of the equation where we have the dV over dt, we'll put -2. And I can go ahead and keep I'll keep my units in here, I guess. And then on the right-hand side of the equation, we know when h equals 3 feet. That was identifying a moment in time, and now we can substitute that in. So we have 4/9 pi, and then 3 feet squared times dH over dt. So that's our substitute step. And now the only unknown left in our entire, make it green actually. The only unknown left in our entire equation here is the dH over dt. And so that's why the last step is to solve for that unknown. So we end up with just dividing everything here. We get like 9 over 4 pi. We have -2 cubic feet per hour in the numerator. And then we have 3 feet. Actually, it's going to be, if I square the 3 feet, I get 9 square feet. And that's equal to my dH over dt. So let's see, we can simplify this up a bit. 9s cancel. 2 goes into 4 twice. And then looking at the units, feet squared cancels with feet cubed to give me just feet, right? So what I end up with here is my final answer, dH over dt is -1 over 2 pi feet per hour. And that's my answer. And if you want to get a numerical version of that, you can pull out your calculator and ask, or you can ask your AI chatbot, what's -1 divided by 2 pi? -0.16 approximately. And that's how fast the height of the is of the water is going down. And actually the fact that it's a negative rate of change means that the water level is going down, which we should have expected if the water is leaking out of the tank. Tony asks his question. We got where did we get that 3 feet squared? Hang on a second, Adam. We're going to answer Tony's question. Part of the original question was, when the height is 3 feet. So that got substituted into this H right here. So that's where the 3 feet squared came from. Was that what you were asking? There it is. Yep. Good question. So Adam, you had a question too?
I have a question. How'd you solve it though? I don't understand the numbers that you use to solve that substitution equation.
Just dividing by everything we know here. So like, for example, here we have 4/9, so I did 9/4, right? I basically multiply both sides by 9/4 to cancel out. The pi was in the numerator, so I'm going to divide both sides by pi, so now pi is in the denominator. We had the -2 already on this side, so there it is, still in the numerator on the left side, but then we divide by 3 feet squared, so now the 3 feet squared is in the denominator over here. It's just dividing. It's just dividing both sides.
That's confusing.
If that's confusing, you can do that yourself in a different way. Like basically you're just dividing both sides of your equation by all this stuff, by the 4/9 pi 3 squared, right? You're dividing both sides by that. And so you can do that in your calculator if you need to. You'll still get the same final answer down here. And what I usually do for problems like this is ask you to give me a numerical answer rounded to like 2 decimal places or something. So it doesn't matter if you do these last few steps in a different way than I did. Okay. Hannah asks a question in the chat. This is about like notation. When you are over here, can you write this in the form, what is dh over dt like of 3? Question mark? Like that? Is that what you're asking? Yes. You can sort of do that. Yes, you can. Like, yes, that is fine. Although I want to caution you here because h is the name of a variable, whereas this is using what you're suggesting here is using the name of the variable like the name of the function that it is tied to. And it is very common practice to do that. Like, okay, so like sometimes in other situations when like x is a variable, you might see if x equals f of t or whatever, you might see like x of t, where you're using the variable's name, x, like a function name, x of t, because x is a function of t, and this is just a sort of shortcut to describe, to like notating that without having to introduce the name of another letter to represent that function. You use the variable as the function. This is a little bit weird because a variable and a function are not the same, but it's, like I said, very common practice to do this, just because I think it sort of streamlines all of the notation, especially if you have a lot of these floating around. If you have a lot of different functions and you don't want to have to like be flipping back and forth between calling the letter, like the variable name and the function name, having different letters for them, like it's very common. So yeah, like you can do this, that's fine, but just if you're gonna do that, I just want to make sure that you understand this concept, that like you're using the variable's name h as like basically as the name of the function as well. So I generally recommend against doing that at this stage in your education, but like certainly later on, it will be very common practice, especially when you get to like parametric descriptions of things in multivariable calculus. You use x of t and y of t all the time. This is for parametric descriptions of curves and things. Good question.
Tristan, do you mind if I ask you something?
No, not at all. Of course, go ahead, Frel.
Do you still take math classes?
Do I still take them?
Yes.
No, I haven't taken a math class in a long time. That's a good question. No, I don't. I got my master's degree like 10, 12 years ago now, I think. And I haven't taken a math class since then. But what I have done is taught classes that I hadn't taken in like a long time. Like I just started teaching linear algebra a couple of years ago, and hadn't taken linear algebra since like undergrad. And so sort of relearning that, let me tell you, you know, you learn a lot more about a subject by teaching it than you do by taking a class. So I feel like I've learned more about math in 10 years I've been teaching than I did in the 10 years I spent in school. Anyway, let's go ahead and do another example, folks. Oops, that's not right. Where I put these here. It's the 28th today. All right. Let's do some trigonometry in this one. Example 2. Here we are, standing on the ground, and we are going to watch a balloon launch. So here's the balloon, and it goes up, and here it is a little higher, and here's the height of that balloon, okay, in the air. Well, let's track the basket. Let's pay attention to the height of the basket there, h. And we are looking, let's just assume that we're at like ground level. Okay. So we're looking at the balloon, okay, and we are going to pay attention to this angle, theta. Okay, and we're gonna be sort of paying attention to the relationship between the angle theta and the height of the balloon h. Now, in order to describe this relationship, we do need to know more precisely how far away we are standing from the balloon. So let's say that distance there, we know where we're standing, we know how far away it is from the balloon launch. Let's say that's like 1,000 meters. We're going to work in meters this time, okay? This is a right angle, and we're going to go ahead and assume that the balloon goes straight up so that it doesn't drift sideways. So this triangle that's formed is a right triangle, okay? So now, given this setup here, what we're going to say if the rate of change in, let's say, the angle is like 0.01 radians per second. If that is the rate of change in the angle at a moment when the angle is, let's say, half a radian. Okay, notice I'm doing everything in radians for us. If I had done this stuff in degrees, we would have had to convert to radians. Okay, so I could be giving you this information in like degrees per second and degrees, but we just immediately convert them. So I'm just giving it to you directly in radians, okay? Okay. What is dH over dt at that time? That's the goal here. Okay. So let's look at the question again. If we measure the rate of change in the angle of elevation here, that theta angle, if we measure that, and we measure it at a particular moment in time when that angle has a specific value, then that's like a snapshot of the angle and how fast it's changing. Okay, this is something that it's kind of hard to do, but you can at least estimate it, because it's kind of hard to measure like exactly the speed of something and also its value, its position at the same time. In fact, actually, there's a name for that. It's called Heisenberg's uncertainty principle, that like technically you can't know the position and the momentum, which is kind of like related to the velocity of a thing like simultaneously, but we can estimate it. Okay, we're not talking physics, like we're not talking quantum physics here. We're just talking like real world. You take some measurements out in the field. Okay, so we got those two things. Now we want to know at that moment in time, how fast is the balloon rising in the air? Okay. Well, what we can do is set up an equation. We already have our diagram and we already have our rates here. So we're already 2 steps into the dreads situation. So let's do equation. We just need an equation that relates to theta and the h. So, my friends, trigonometry. What is your trigonometry relationship that will involve the angle, the h, and the one other piece of information that we have here, which is the distance we standing from the location of the balloon launch on the ground?
Something with SOHCAHTOA, right?
Yep, it's one of the three. It's either sine, cosine, or tangent. Justin gives us a suggestion in the chat to go with tangent. Anyone else want to weigh in on that decision?
Tangent.
Ooh, we gotta vote for cosine. Let's review SOHCAHTOA real quick. Sine of the angle is going to be opposite divided by hypotenuse. Cosine of the angle is going to be adjacent divided by hypotenuse. And tangent of the angle is going to be opposite over adjacent. So let's put a question mark here. We don't know anything about the hypotenuse of this triangle. We don't know anything about the hypotenuse. What is the hypotenuse? I don't know. So we really don't want to use sine or cosine because they involve the hypotenuse, and we want to avoid our hypotenuse. But we do know the opposite. We don't know the opposite. The opposite is what we want to find out about, right? And the adjacent. So yeah, tangent is indeed our winner there. Okay, good review. So here's how we set up the equation. We set it up as tangent of theta equals the opposite side, which is h, divided by the adjacent side, which is 1,000 meters. Okay. So there's our equation.
Shouldn't it be tangent of 0.5 radians?
Good question. Should I plug in 0.5 radians yet?
I mean, not the actual 0.5 radians, but you know, the degree, what it would be in degrees.
We don't want to convert to degrees. We can keep everything in radians. So for the tangent function, you can just set your calculator to radian mode, and then it'll expect the input to be in radians. So there's no need to like convert the input to degrees just for the tangent function. You know, it doesn't need it to be in degrees. As long as you put your calculator in radian mode, then then you know it'll be okay.
Well, you could just multiply by 1,000 meters to both sides, right?
We could if we wanted to. Yeah, we could certainly do that. We could say 1,000 meters times the tangent function of h of theta equals h. Yep, that's fine. We could at least do that if we want to. But the question that you asked, Frau, which I think is really, really worth discussing, is should we do that?
Well, I mean, if we want to find the opposite, no, if we want to find the opposite, should that be the idea?
Are we trying to find the height of the balloon?
No.
What are we trying to find?
The hypotenuse?
Oh no, we don't care about the hypotenuse. We're not asking about the hypotenuse.
You mean dH over dt?
That's right. Let's look back at our goal. Our goal is this. What is dH over dt? Is that the height of the balloon? It's not the height of the balloon. It's the rate of change in the height of the balloon. It's how fast the balloon is rising, not how high it is. Right? So if we wanted to know the height of the balloon, we could plug in 0.5 radians and calculate the height of the balloon. We could do that. But that's not really our goal right here. Is it? Our goal is to figure out the rate of change. And if we're going to do a rate of change, we need to take a derivative. Okay? And here's the thing, if you're going to take a derivative of an equation, you better make dang sure that variables are still variables. Only plug in a value for a variable if it is truly constant over time. So my question for you then would be, is theta constant over time, or is theta going to be changing?
Well, it changes from when the balloon's on ground level to when it's in the sky, right?
It
But we're
sure
measuring
does.
Yeah.
Yeah, like it's going to be going up like this, right?
Yeah.
Like as the balloon rises, theta is going to change, right?
Yeah. So you can't plug it in because it's not constant.
That's right. You can't plug it in. We do not want to do that. I'm going to put not yet right there. Not yet. We will do that later. That's what the substitution step is for. It's like, that comes after differentiate, right? Then you substitute. But we're not ready to do that yet. All right. So yeah, we need to differentiate. Let's go ahead and take this version, 1,000 meters times tangent of theta. So 1,000 meters is a constant, so that's still there. Then we had to differentiate tangent of theta. The derivative of tangent, as we may remember from chapter 3, is secant squared, right? So we've got secant squared theta. But then since we're differentiating with respect to time, we multiply by the derivative of theta with respect to time, like that. And then on the right-hand side, that's dh over dt. So the substitute step is then to plug in any known information we have. So now we get to plug in this information. Okay.
Can I ask a question before you move on to the next one?
Yep.
So whenever we used to differentiate, if there was a constant, you would just like basically turn it to 0, right?
Whoa. That's for a constant term. If you're differentiating a constant, then yes, then its derivative is 0. But if it's a constant multiple, we have always treated that with the constant multiple rule.
Okay.
Remember? That's why, like, when you do the derivative of, like, 5x squared, you don't get, like, 0 times 2x or something like that. No. You get 10. You get 5 times 2x. You get 10x. Right? Because the 5 is a constant multiple. It's not a constant term. So if you were doing the derivative, contrast that with the derivative of 5 plus x squared. That would be 0 plus 2x. That's fine.
Right. Because they're multiplying, so you leave it. Okay. Yeah. Thanks.
It's multiplying. That's right. So technically what you could do here is you could apply the product rule, and then you would end up with 5 times the derivative of 2x plus 0 times x squared. And then the 0x squared goes away and you just get 10x. So yeah, you could, yeah, it's because it's multiplying. That's the reason it's different. All right, so we're plugging in our 0.5 radians now. We also get to plug in our 0.01 radians per second for the rate of change. So what we have now is 1,000 meters times secant squared of 0.5 radians. Make sure your calculator's in radian mode, times 0.01 radians per second. And that's going to equal our final answer, dH over dt. So now the solve step is just to plug all that in the calculator. Let's make sure we can do that properly, and then we'll be done. We're out of time. So if you guys got to get going, that's fine. I'm just going to plug this into the calculator. If you're doing well, you guys are probably going to be using like Desmos or something. I was going to show you how to do it in Google. Have I told you Google search bar is my second favorite calculator after Desmos? Because it's just always there. It's so accessible. We have 1,000 times secant of 0.5 radians. And I believe, yeah, Desmos is in radian mode by default. If you want to change it, you have to do this. But we keep it in radians. We got to square that secant function. And then we'll multiply by 0.01. And our answer is 12.98. So dH over dt is 12.98 what?
Meters?
Just meters?
Meters per second.
Meters per second. You look back at our units. If we sort of pay attention to the units, it was meters here. Here we had here we had secant. If you do secant, if you do a trig function, what are the output units? Trick question. The answer is nothing. Because a trig function, whether it's SOHCAHTOA or one of the reciprocals of those, these are all like meters divided by meters. They're all ratios of sides, right? Of side lengths. So whatever those side lengths are measured in, meters or feet or inches, doesn't matter, cancels out. And the output of a trig function has no units. So the secant squared doesn't contribute anything. We got radians per second, and the second is in the denominator over here. What about radians? Shouldn't it be like meters times radians over second? Does anyone remember anything about radians and how they work as units? We're running out of time, so I'll tell you. No, radians are a unitless measurement, just like the ratio of that for a trig function output. They don't contribute to the units of an answer. And the reason, because radians are defined as a ratio of lengths as well. So just like how it would be meters over meters cancels out for the trig output. Radians are also, they're like an arc length divided by a radius of a circle. And that's a length divided by a length. And so the units cancel, same as trig outputs. So yeah, that doesn't really contribute anything. So we really just have, this is our answer, 12.98 meters per second. And there we go. All right, folks, have a lovely day. And we'll see you tomorrow.